Got it. Okay. So now we continue with this geologic sections. We will change the context a bit. The overall context remains the same. But I will bring in igneous rock forms into it. And then we will try and see what we can do about it. So it's about igneous rock forms and geologic sections. Last time we studied igneous, we studied unconformity and geologic sections. Now we bring in igneous forms and geologic sections. And then I will give you more complicated geologic sections to do, which you have to send me over time. Now, as I told you before, igneous rocks can be deposited as form as plutonic rocks that crystallize below the Earth's surface, and igneous rocks that crystallize above the Earth's surface from lava flows, and these are called volcanic rocks. Here we will talk mostly about forms of plutonic rocks. Let me draw a block diagram. Now, there are several forms of igneous rocks. I will write them down. I will tell you a little bit about some, and I will leave the rest for you to study. One is called a dike. One is called a sill. The other one is called a batholith. The other ones are called stock, and then facholiths and lopoliths. These are forms of plutonic igneous rocks. I will tell you about this three. And this three you will have to learn yourself. Yes, I will tell you about this. You have to learn about stocks, facholiths and lopoliths. Now, let's say there is a set of sedimentary rocks. As you can see, these are a set of sedimentary rocks. This is the top. Let's say this is the north. This is top. Right? And simplifying, oldest, youngest. Why? We will come to that later on in the lecture. I will draw a few things and tell you I will draw Now, I have drawn a dike, a sill, and a batholith. Sedimentary rocks with horizontal layers. And on both sides, I have made some dots. Dots. This is called contact metamorphic zones. I will explain it to you what it is. But first, what is a dike and what is a sill? Let's take sill. The sill, all these are intrusive igneous rocks. Intrusive igneous rocks. That means they crystallized below the earth's surface. A sill is an intrusive body which is a planar habit. That means its thickness is much small compared to the length and the breadth. Have you understood? So that's how a sill is. A sill is an intrusive igneous rock body which is planar in shape and its width considerably small compared to its length and breadth. This is true not only for the sill, but it is also for the dike. Both are planar bodies with the thickness much smaller compared to the length and the breadth. Have you understood? This is a characteristic of both dike and the sill. But why the difference? Why the difference? The difference is the sill, you can see, it is concordant. Concordant means having the same structure as the intruded sedimentary rocks. Have you understood? So the orientation of this planar body, which I call sill, is concordant with the structure of the rock into which it is intruded. That's the point. Concordant. And you can see here a dike. The dike is a planar igneous body with the width much less than the length and the breadth, but it is discordant to the structure of the intruded rock. Have you understood? That is the difference. Dike is discordant to the structure of the intruded rock, and sill is concordant to the structure of the intruded rock. Both are planar bodies. And this is called a batholith. A batholith is a large igneous body, which has intruded, which is non-planar in shape, and it has intruded in the shape of a dome into the existing crust. So on plane surface, a batholith is mostly circular to semicircular to elliptical in shape. There are no limits to it, but there are very big in size. For example, you know, in America there is a place called Sierra Nevada batholith, which is 80,000 square kilometers in area. 80,000 square kilometers in area. That is the dimension of the Sierra Nevada batholith. And that's very, very big. This you are seeing as a cross section. If this was exposed on the planar surface, it would look circular or elliptical or semicircular in shape. Now, what are these dots? Now you see, igneous rocks are hot material. When they intrude the rocks, generally, the intruded rocks are colder. So what happens? These hot igneous bodies release heat to the surroundings. So what happens? These host rocks adjacent to the sills and the dikes and the sills and the batholith, because of the heat release, these rocks neighboring it is heated to high temperatures as well. So these are essentially metamorphosed rocks. That is why I have given these dotted lines. Have you understood? This is a dotted lines. The dotted line indicates that the neighboring rocks adjacent to it were heated. Now you can ask me, so what is great about it? Now, let me draw a small addition to this diagram. Say, for example, this was another rock. And I did not draw the contact effects. So, how will you prove that it was an intrusive rock? Because if it was an intrusive rock, that means there were rocks on either side and it intruded through it, and therefore it should have heated up the rock. But I did not show any heating up on either side. So now you're in a bit of dilemma. If I drew the contact metamorphic effects on both sides of it, then you would immediately say, okay, it was a sill, it was an intrusive body, it heated both sides of it. But say, for example, if I just drew this, that means the contact effect is restricted to the lower part of that body. What would that mean? This would not be a sill. This would never be a sill. Why? Because if it's a sill, it should have heated both parts because it's an intrusive rock. But I have shown the contact effect at the lower part of the body. So what does it mean? It was a lava flow. Because when the lava flow occurred, it heated the base onto which the lava flowed. But the lava, when you have a lava flow, it's on the earth, on a basement. There was nothing above it except water or air. So it could not have heated a rock above it because there was no rock. This would mean that it is a sill. It is a lava flow. So when sedimentation was going on, say when A was deposited and then B was deposited, this flow, lava flow, deposited on B, but C was not there yet. C deposition did not come. C was deposited after the lava flow cooled. Do you understand this? So that is important to know. That where is the contact metamorphic effect? If it's on both sides, then it could be a sill or a dike, depending upon whether it is concordant with the host structure or discordant with the host structure. But in case of a lava, it will only hit the lower part, because that rock was there. The rock above it wasn't there, so there's no question of heating it. So it would have cooled very fast, because the temperature of magmas are very high. As I told you, 700 to 1000 and even more. 1200 degrees centigrade magmas are known. 1400 degrees centigrade magmas are known. Of course, those magmas do not occur anymore. But there are temperatures rise from 700 to 1400 degrees centigrades. And they're very high temperatures. And when they come in contact with air or come in contact with water, they cool very rapidly, very fast. And you deposit sediments after that. It's not very heated. So we have studied dikes, sills, batholites. Batholites. Now there is also another example that I will give you. This example is not to give at this stage, but I will tell you, because we will come to this later on. You see, all these dikes, sills, batholites, whatever I have shown you in two colors. It was not accidental. All these dikes and sills, they are shown in black colors, or lava flows. They are shown in black colors. But this batholith is not shown in black colors. It's shown in white colors. Because batholiths are formed by magmas which are very viscous. Why? We will talk about this later. It is because of the silicon-oxygen bonds, which are strongly covalent bonds. They have tremendous polymeric constitution in this batholith forming magmas, which are called felsic magma, silica-rich magma. Silica-rich magmas are very, very viscous, so they cannot flow to a great extent. But these dark ones represent, one is called felsic magmas. Felsic magma, they mostly form batholiths, and mafic magma, these are silicon rich, SiAl rich, and these are MgFe rich. Now these mafic magmas normally are not viscous, they are highly fluidized. They move very fast. So that is why I have given two colors, because if there is more iron, the materials would look darker. If there is less iron, the materials would look less colored. That is why I have used these two symbols. This is just for the beginning. What I mean is, silica-rich magmas, because there is abundant, it's essentially a polymer of silicon, oxygen, aluminium framework structures, whereas mafic magmas are less viscous because the silicon oxygen bonds are broken and they are more fluidized magmas. So for example, when you have volcanic eruptions of mafic magmas, they are called silent killers, because these volcanoes, when they come up, these mafic lava flows, they flow down the hill at terrific speeds, up to 60 kilometers per hour is the speed of this, depends on also on the slopes of it. So they produce very fast moving lava flows. So you might have heard of many famous volcanic eruptions which killed cities, drowned cities, killed thousands of people. But felsic magmas, if they come out of volcanoes, they are not so viscous. But they are charged very much. They are very much charged with gases and very polymeric, thick material. So they can't flow, but they are very explosive in nature. Very, very explosive in nature are these silica aluminium rich felsic magmas. Whereas iron magnesium magma, because it's less polymeric, because it's less viscous, they can move fast and they can kill. They can overrun cities. But thousands of people can be killed and they wouldn't be awake in the night and they would be completely burnt in their death and no one would know. There are many, many such instances happened in the world. Now we use some of these structures to interpret geologic sections. Say for example, I said a problem. A dike is intersected by two normal faults. One older than the other. Say this a question. A dike is intersected by two normal faults, one older than the other. That means if the dike is intersected by two faults, that means both the faults are younger to the dike. Both the faults are younger to the dike. And the dike must have intruded some sort of a rock before, because otherwise you can't have a dike, because dike is an intrusive rock. There must have been an older rock, although I have not mentioned what is the older rock, but there has to be an older rock. That's for sure. And it is faulted by two normal faults, one older than the other. One older than the other. How would you draw the section? How would you draw the section? So, let me start. So, here is a geologic section. Let's say I have a dike. I have a dike. It is faulted by two faults, by two normal faults, one younger and one older. Imagine, one younger and one. From this, that the two faults are younger than the dike. And the dike has intruded an older rock, although that older rock finds no mention. But you have to show that there was an older rock. Isn't it? So, how do I do it? Say, what did I do? This is the dike. I have faulted it by a normal fault. Yes or no? This is very clear. One dike and I have faulted it. You see the hanging wall has gone down related to the footwall. So I have faulted the dike but once. But it says there are two normal faults. One younger, one older. So I have to establish a relationship. That dike, the one more dike that is left to draw, it should intersect the dike and it should either be younger or older than the fault. Yes or no? So what I do is, here look, what I am trying to do, this is fault 1. Now you see what I am doing. Now you see what I've done? This is the dike. This is the dike. It has been faulted normal. This has also been faulted normal. Both are normal faults. But you see what I have done? This is fault F2. The F2 is faulted by F1. Have a look. The F2 is faulted by F1. Tell me, have you understood it? So, it is like this dike F2, F1. This is direction of Young. F1 faults. Both the F1 and F2 has faulted the dike. No doubt about it. It has been faulted. But here I show that F1, this one is F1. This one is F1. This F1 faults F2. That means F1 has to be younger because it has faulted F2. And this one, F2, F1 and F2, since it's above, dike is older, these two are younger. That means both F1 and F2 has faulted the dike, which is true. But F1 has faulted F2, so F1 is younger. Now, what remains? We have said dike, but there is no proof. There is no proof that it is a dike. How will you prove it that it's a dike? It has to be discordant to the existing structure. It has to be discordant to the existing structure. So, you can see here, if I A, B, now you see here, I'm drawing AB, what will be, how will B continue here? You see here, B, this is a normal fault. This is a normal fault. B, this is a normal fault. So if so, B has to be here the boundary, this boundary, this, let's say, I will do it the other way. Let's write C, B and A. Here you see, this is B. You see the drop. This is B. What will be the B? Where will the B go here? This is a normal fault. If this is B here, then the B should be here somewhere. And therefore, this should be B. And this should be C. And this should be B. And then this should be A. And somewhere this should be. You can add D, etc. depending on what you want to add. So there is A, B, C sedimentary rocks. So you have a set of sedimentary rocks ABC. See, this is C. These are all C. This is B, tapered off. It appears again. With respect to this, B is down. With respect to this, did I do it right? No? I have did it wrong. Sorry. I have, you know what I've done. This, when I say this is gone down in a normal fault, that means there has to be a slight angle onto the right. If I tilt this angle onto this, it will show you reverse fault because you have changed the footwall at the angle wall. So this is how geologic sections are. Okay, a dike is intersected by two normal faults, one older and the other one young, older than the other one. So you have a dike intersected by F1, F2, but it is not said, but you have to say that it's a sedimentary rock because you have to prove that it's a dike. That means it is discordant to the horizontal sedimentary rocks, or not horizontal, the existing structure of the intruded rock. That you have to prove. So now you can see with these two faults and these igneous rocks, it's already become very complicated. Previously you saw with the angular unconformity and the faults, it became very complicated. So now if I ask you, if I combine igneous forms, unconformities, sedimentary rocks and faults, it will become very, 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 very complex. I will send you through classroom, through Google Classroom, some of these sections as images, and you need to do it. Okay, let's try and see a simple one. Let us think of a simple geologic section which we can handle. Say we have a angular unconformity, a normal fault, and a dike. The dike is older than the unconformity. And the normal fault is younger than the unconformity. So, there is an angular unconformity. Now we know if you have an angular unconformity, you have to have two sets of beds separated by an unconformity. Then you have a normal fault which is younger than the unconformity. Younger than the unconformity. And there is a dike older than the unconformity. So if we try to place this as a sequence, how will we place it? First of all, the fault is younger than the angular unconformity. This is younging, yes? This is younging. So fault is younger than the angular unconformity. And the dike is older than the unconformity. That you have to prove. That you have to say. These are the facts that it has been given. But we should also know that the dike intruded angular unconformity means there are sedimentary rocks above and below. So below, if there is an angular unconformity, a dike cannot be placed in a vacuum. It has to be enclaved. It has to be placed in some sort of a sedimentary strata. So let's say there was A, B and C sedimentary rocks. This sequence was there, into which the dike was intruded, and the dike was older than the unconformity. That means the angular unconformity was not there, and then there's a fault that falls. So how do we draw the geologic section? So now you see here, dike A, B, C, D, E, F, G sedimentary sequence. Then you have angular unconformity. Then you have a set of sedimentary rocks, M, N, P. So you will have M, N, P sedimentary rocks. And then there has to be a fault. Now, since this is a fault is the youngest, it will fault everything. It will fault everything. So, what type of fault? Normal fault. So let me have, let's say this is the fault, FF. Now if this is a normal fault, you can see what will happen on this side. You see that? Look at this diagram for some time. See what I have done. You had a sedimentary sequence A, B, C, D, E, F. A sedimentary sequence, inclined beds, and a dike cutting across it. But the whole thing was truncated by this angular unconformity. So, the first rocks that they were, A, B, C, D, E, F, sedimentary rocks, into which a dike had intruded, and then the whole thing went above water, and there was erosion, and when erosion, the top part of the dike got cut off, truncated because of the erosion, and then there was deposition of MNPQ. There was deposition of MNPQ, and then the whole thing was faulted by a normal fault. So what happens? The unconformity plane faulted from here to here, the MNN boundary here, PN boundary here, and a new rock came in here which was not observed here. So this is what you see from a geologic section. It proves all the points that you have. So what I have been trying to establish so long, and here it is, that using geological, by knowing the backgrounds of geologic structures, how they form, if you have an idea, and if you see interference of these geologic structures, we can find out a relative time over which the structures have developed. We can do it on plan view, we can do it on section view, because you are quite you're not very trained in geological maps, which can be very complicated. So I am showing it on a geologic section for you to understand. Now you must understand another thing, that first there was a sedimentary sequence, so the sequence was below the mean sea level, there was deposition of sediments. Then there was a dike emplacement which cut it. Then the whole sequence went up So you had an angular unconformity. So a part of the history that it was, it must have been eroded off. And then again, the whole thing went down and you had deposition of MNPQ. And here you see this, then there was a faulting and the whole, this hanging wall part went down relative to the footwall. Important thing is here. You see, if you are here standing here, there is no evidence of P, no evidence of Q. But if you are standing here, you are standing on Q. And what is this? What is this ground at the top? This is a present erosion surface. Present erosion surface. This is the present erosion surface. The ground on which you walk is an erosion surface. It's above the mean sea level. Materials are being transferred from there. So what is happening is, at this point you see you can record till P. But if you are here, you get an idea. No, the sedimentation continued for a longer period of time in Q. It may have prolonged even long. But there is no evidence. There is absolutely no evidence in this geologic section whether the sedimentation of younger bed continued for a longer time till Q. There is no evidence. Because the whole part is removed. Maybe MNPQ, RS, TXVZ, it all deposited, but the whole thing went down because whole thing was removed. You can imagine another thing, that you have these high Himalayan mountains from where you have the Ganga, the Jamuna and the Brahmaputra bringing. It has been measured over the last 50-60 years that Mount Everest, the height of Mount Everest has not increased at all. Can you tell me why? Because Mount Everest is so high and there are so many rivers coming down these slopes, they must have eroded it away. No. If it has, the height of Mount Everest did not decrease. Why? It is because the amount of erosion, the materials that were brought up, and the land, because of the collision of the Eurasian and the Chinese plate, because of this contraction, materials are going up. So there is a perfect balance of Mount Everest, that it is something is pushing and squeezing it up, and the rivers and the hills, they're bringing the whole thing down. And this is absolutely at par. So the peak of the Mount Everest has not changed over the last 50 to 60 years. There's a perfect balance between subduction zones, as you call it, and erosion. There is a perfect balance. Now recently there has been an idea to measure the Mount Everest again by India, Nepal, China, but I guess something has gone wrong there. So they have a problem. But there has been now an international effort to measure the peak of Mount Everest once again. And they would like to put some materials there so that they can find out the change in height over time. Okay, then we come to the end of this restructuring of the geological records. We will continue to do the geologic sections, and I will take back feedback from you. But next class, we go over to what is called geochronology proper. Not relative time, but how is absolute time found for particular events in the history of the earth. That we will do in the next class. Thank you.